Hi everyone, my name is Shani Harris and welcome to Surviving Math with Shan. So this video will entail the review of counting, and more specifically we'll be looking at the Assesed tutorial sample. Of course the solutions are there, but one thing you should note with this course, because we've been told this several times, is that the process, how do you get to your solutions, is more important than the solution itself. So that is what we'll be discussing in this video. So before we actually get into the video, let me just share this. I spent the first few classes of discrete mathematics very confused. I was extremely lost, guys. I'm not even gonna lie to you. I spent the classes, I was looking around to see if I was the only one that was lost. If I was just having a bad day, like nothing was registering to me. Yeah. After like going to 2 tutorial classes, because that's what I did, and just keep on practicing, going through tutorial 1 again, going through tutorial 2, the Assesed tutorial sample, I can see my understanding has improved a lot, which is why I feel the need to share it with you guys that might be still unsure of how do you approach these questions, and how do you know if order is necessary or order is not necessary, if there's some sort of repetition, what formula you should use, just overall analyzing the questions better. So without further ado, let's get into the video. I'm done talking. Well, I'm gonna be talking for the whole video, but you know. Suppose we have the digits 4, 3, 5, 7, 8, and 9, and repetitions are not permitted. A. How many 3-digit numbers can be formed? Okay, so first of all, with these questions, the first 2 questions you have to ask yourself is, does order matter, and is there repetition of any element, or is repetition permitted? So once you can answer those questions, you can proceed with the problem. Okay, so we know that repetition is not permitted because the problem stated it's not permitted. So all we have to do is figure out whether or not order matters. And figuring out if order matters or not, it lets us know whether or not we're dealing with a permutation or a combination. So here we have the placements for a 3-digit number, and we choose to put down 4, 3, and 7. When we switch around the placements of 7 and 4, or even 4 and 3, we realize that each time we get a different number, which tells us that order is important. So with that being said, we know that order matters. So we're dealing with permutation. So since we're dealing with permutation and repetition is not permitted, all we have to do is follow the formula for that. So we have NPR. So N represents the number, the total number of selections, and R is what you're actually choosing. So from the question, we have 6 digits. We have 4, 3, 5, 7, 8, and 9. And the question is asking us, part A is asking us for 3-digit numbers. So with that being said, N in this case would be 6 and R would be 3. So our answer to this question would simply be 6P3. And of course, there is another way you can analyze this. So let's get into that. We want to place our digits, and let's say the hundreds place is our first place. We have 6 options to choose digits for the hundreds place. We choose to put down 9, we're left with 5 digits, meaning we have 5 options for the tens place, and we choose to put down 7, just for example, and we're left with 4 options for the ones place. This would mean our answer would be 6 times 5 times 4, which is the same thing as 6 permutation 3. 1B, how many are even? The last digit of any even number is 0, 2, 4, 6, or 8. So from our selections, we're seeing 4 and we're seeing an 8. So these are the only 2 options of numbers we can place in the ones column for the whole 3-digit number to be even. So when we're placing the number, we can only place one at a time. So either we're placing the 4 or we're placing the 8. So when we place one of these numbers, we're left with 5 options for the hundreds place and 4 options for the tens place. And of course, we multiply to get our solution. Question 1C. How many of these 3-digit numbers are less than 500? So with this question, we're looking at the number in the hundreds place. So since we're looking for numbers that are less than 500, in the hundreds place, we would expect the digit to be less than 5. So from our selection, we're seeing a 4 and we're seeing a 3. These are the only two digits from the selection that are less than 5. So those two digits, we can for sure put it in the hundreds place. But of course, we wouldn't put it at the hundreds place at the same time because that wouldn't make sense. Yeah. Question 2a. Determine the number of strings that can be formed by ordering the letters FIRST. Which is first? Okay, so with this question, it's telling us that we're ordering the letters in the word first. Since it specifically said that we're ordering letters, we know immediately that it is permutation. So we know order matters. So now we just have to figure out if repetition is permitted or if there's any repetition of any elements. So in the word first, no letter is being repeated. That would mean there's no repetition. And now we'll just ask ourselves, is repetition permitted? Well, we're ordering the letters in first specifically. So we can make the assumption that since we're dealing with these letters in the word first, repetition is not permitted and there's no repetition of any element. So with that being said, since there's 5 letters in the word first, I would just want to switch around the order of each letter, see how many times we can do that. We're just following the general formula that we know for permutation with distinct elements, and that would be n factorial. So our n in this case would be 5, so the answer to this question would be 5 factorial. So that would be the reasoning to that. Question 2b. Find the number of permutations that can be formed from the letters of the word 11, beginning with the letter E and ending with the letter N. Okay, so of course we're asking ourselves the general questions that we always ask ourselves when we're dealing with these questions. Does order matter? Is there any repetition of any element? First of all, immediately from the get-go, we know that order matters because the problem is asking us to find the number of permutations. Permutations, order, yeah. And of course, is there any repetition of any element? So we have the word 11. In the word 11, we have 3 E's. So of course, we know that there is repetition. Finding the number of permutations that can be formed from the letters of the word 11, beginning with the letter E and ending with the letter N. So from the get-go, we know that since 11 has 6 places, 6 letters, right? We know that in the first place we're going to have an E, and in the final place, being the 6th place, we're going to have an N. So it's just a matter of how we're arranging the 4 letters, those 4 places, and just the 4 remaining letters, which would be L, E, V, E. So since we have an E in the first place and the N in the last place, we know that the possible outcomes for the first place and the last place would be 1. So now our focus is the 4 remaining letters, L, E, V, E. We're going to ask ourselves the question again, is there any repetition? The answer would be yes, because we're seeing 2 E's. Therefore, since we know order matters and there's repetition, we'll be using the formula that deals with permutation with repetition, which would be n factorial over n1 factorial, n2 factorial, and onwards. So of course, the n factorial in the numerator would be the total number of letters we have there, which would be the 4. So in the numerator, we would have 4 factorial. And with the n1 factorial, n2 factorial in the formula, this is simply the amount of times we're seeing a repeat of our letters. So right here, we're just seeing the E being repeated. So the only repetition we'd have in the denominator would be 2, and of course we have factorial. So it would be 4 factorial over 2 factorial, and our answer would be 1 times 4 factorial over 2 factorial times 1. And just to add on why it's so important for you to acknowledge that there's repetition in the problem, let's say we know that the word begins with E and it ends with N. So in between, let's say that we actually said, oh, this E is E1 and this E is E2, right? So in one of counting the permutation, right? One string that would be counted would be perhaps E1, E2, LV, N, right? However, the permutation, the formula would also be counting, if you didn't acknowledge that there's repetition, it would also be counting E, E2, E1, L, B, N. So we'll be counting those two strings as different when E are E. So this is why it's very important for you to acknowledge that there's repetition or not, and yeah. So it's example guys. Question 3. There is a set of 5 distinct art books, 3 distinct mathematics books, and 2 distinct computer science books. A. In how many ways can these books be arranged on a shelf? Does order matter? Yes, because it's asking us for the number of ways we can arrange these books on a shelf. Arrangement suggests that we're trying to figure out, oh, how many ways we can order these books. Put the books in different orders. Yeah. So is repetition permitted? Is there any repetition of any element? So from the question, from the problem, it's saying that there's a set of 5 distinct art books, 3 distinct math books, and 2 distinct computer science books. Note the word distinct. The problem is telling us that each book, although they're the same subject, each book, they're different books. They're the same subject, but they're different books. So that lets us know that there's no element, there's no books being the same, so there's no repetition. Then we're going to consider each book individually because they are distinct, right? So of course we'll have 5 distinct art books, 5. We'll have 3 distinct math books, 3, and we'll have 2 distinct computer science books, 2. In total, we're going to get 10. So since we know that that's the total number of books, all books are different, the order matters, we're going to use the formula that suggests that we're dealing with permutation with no repetition. And of course, that would be n factorial, and in this case would be 10. So our answer is simply 10 factorial. Question 3b. In how many ways can these books be arranged on a shelf if all books of the same discipline are grouped together? Okay, so now the question is asking us to how many ways we can arrange the books on the shelf with all books within the same discipline, although the books are distinct, but we want them in the same discipline, right? So there's 2 considerations. There's 2 things you have to consider. For one, how are you going to arrange the books in terms of their groups? Whether are you gonna put art first and math second, then computer science third? Are you gonna put computer science first, art second, math third? Or you know what I'm saying, right? So that's one thing to consider. The second thing you have to consider is how are you going to arrange the books within the same discipline? Because you have to remember, each book within the same discipline, they're different. So let's look at math, for example. So here we have 3 different math books, and there's different ways we can arrange these math books on a shelf. So that's what we're considering. So really truly, we can see this whole thing as a process, and with each step of this process, there's different ways we can do each step, right? Which is why, since it's a process and there's different ways to do each step, we'll be using the multiplication principle, where after we find each way, we can arrange the different disciplines, and then the different books within that discipline, we'll just multiply them together. So our first value, so we're finding the amount of ways we can arrange the different disciplines, right? So since we have 3 different disciplines, and of course order matters, there's no repetition because they're all different categories, we're using the formula that we know, which is permutation without repetition, and that would be n factorial. So 3 categories, that would be 3 factorial, times how the amount of ways we can arrange the art books. So there's 5 distinct art books, so we know that would be 5 factorial. We'll move on to math. There's 3 different math books, so that's 3 factorial. And then computer science, there's 2 different computer science books, so that's 2 factorial. So our solution to this would be 3 factorial, 5 factorial, 3 factorial times 5 factorial times 2 factorial times 3 factorial. C3. From a set of 6 distinct history books, 9 distinct classics books, 7 distinct law books, and 4 educational books, how many ways can we select 3 books each from a different subject? Okay, so we're told we have 6 history books, 9 classics books, 7 law books, and 4 education books, and we want to choose 3 books each from a different subject. So each time we're like selecting a book, we're picking 3 books out of the 4 categories. So since we're picking 3 books, right, 1 book from each category, and we'll have 4 categories. That would mean that each time we're selecting a book, one category would be excluded from that selection because we're choosing 3 out of the 4. So in one case, we might have history, classics, and law, and we exclude education. In the next case, we'll have history, classics, we exclude law, and we'll have education. Third case would have history, we exclude classics, and we'll have law and education. And the final case, we exclude history, however, we'll have classics, law, and education. So remember, we want to pick one book from each category until we get 3, and we want to know how many ways we can do this. So since we have 6 history books, that means we can pick any one from the 6. We have 6 options. Since we have 9 classics books, we can pick any one from the 9. So we have 9 options. Since we have 7 law books, we can pick any one out of the 7. So we have 7 options. And since this is a whole process, we're doing them all together, we're multiplying. So we have that for case 1, we do case 2, we do case 3, we do case 4, and this is just based on the number of options we have for each category. And of course, these are different cases, so we'd add in the end. Question 4A. In how many ways can 3 teams containing 4, 2, and 2 persons be selected from a group of 8 persons? General questions. Does order matter? Is there any repetition of any element? So the question is telling us that we're finding the number of ways we can choose from 8 persons to form like 3 teams. One containing 4, one containing 2, and then the other containing 2. Right? Does order matter? So think about it. Let's use this example. We have John, we have Tim, we have Sam. In one case, I can choose John first to be a part of my team. Then I choose Tim, then I choose Sam. But other case could be I chose Sam first, you know. Then I chose Tim, and then I chose John. They're the same people. I'm still working with the same people at the end of the day. So does the order in which I select the people matter? I'm still working with the people. So that means the order wouldn't matter, guys. It's the same people. You just form them in a team. And yeah. Now, is repetition permitted? So from the question, it's 3 different teams. We're assuming it's 3 different teams. One containing 4, one containing 2, and the other containing 2. We don't want one person to be a part of 2 teams. Or, you know what I'm saying? So that would mean, since we have like 8 different people, and we want to form 3 different teams, we're gonna say that repetition is not permitted. There's no repetition. So since we know order doesn't matter, we know that we're dealing with combinations, and of course there's no repetition. So we're looking at the formula that has combinations without repetition, right? So let's look into this question a bit more. So let's say first we select the team with the 4 persons. That would mean we're selecting 4 out of the 8 people already, right? So in that case, our n, being the total number of selections, would be 8, and R would be 4 because that's the actual amount that we're choosing. Next, we'll have one team down. We're looking at the other team, and we want that team to have 2 persons. We'll already choose 4 people out of the 8 to be a part of team 1. So that would mean we'd have 4 people left to choose from for team 2 and team 3. Because of that, we would have 4. Did I say? Okay, so the first instance, it would be 8C4. So for the second instance, since we're choosing from 4 people and we're choosing 2 people from the 4 people, we're going to have 4C2. And of course, after we choose the 2 people for team 2, we're going to be left with 2 persons to choose from for team 3. And since 2 people, team 3 must have 2 people, right? Exactly. It's simply going to be 2C2. And of course, you're multiplying all of them together, because at the end of the day, it's a process. You're choosing members to be a part of 3 teams. You're doing it in a process. It's a process, guys. 4B. In view of a bag containing 20 distinct balls, 6 red, 6 green, and 8 purple, in how many ways can we draw 5 balls, then replace the balls, then draw 5 more balls? Okay, first of all, does order matter? No, because we're drawing 5 balls. We don't care which order we draw the balls in. At the end of the day, we just want 5 of the balls, and all the balls are distinct. Yeah. Is there repetition? No, because all the balls are distinct. So there's no way for us to choose 2 of the same balls, 3 of the same balls. No, because they're all distinct. Regardless, they're the same color, they're distinct. They might have a different pattern. You know what I'm saying? Yeah. Next question is asking us to find the number of ways we can draw 5 balls, then replace them, and then draw 5 more balls. So since we know that order doesn't matter and there's no repetition, we know that we're dealing with combination without repetition. And because of that, since we have 20 distinct balls, that's the total number for our selection, 20 would be our n. N would be our 20. N is equal to 20. Yeah. And we're selecting 5 balls out of that 20. First, we're selecting the 5 balls. So R would be 5. And of course, the question said that we replace the balls and then draw 5 more. Right? So first step, we select 5 balls. Second step, we replace the ball in. Third step, we're drawing 5 more balls. So since we replace the balls, right? So in the first step, the number of ways we can select 5 balls from 20 would simply be 20C5. Next, we want to draw 5 more balls. However, we replace the balls that we took away already. So really and truly, since we're just drawing 5 more balls, we're literally doing the same thing over again. So it would be 20C5. So all we do, we're multiplying the two. We have 20C5 times 20C5. And of course, you can put that in brackets and just have 20C5 all squared. Question 4C. In how many ways can you draw 5 balls without replacing them, then draw 5 more balls? So of course, this time we're not replacing the balls. So of course, our first step, we draw the 5 balls from the 20. So we know the number of ways we can do that would be 20C5. Next step, we don't replace them. So that means when we're drawing 5 more balls, we're drawing from 20 minus 5, which would be 15. So that would mean our answer would simply be 20C5 times 15C5. So that's the simple reasoning to that question, really and truly. The solution is there. And of course, yeah, this is one of the easier questions. Question 5A. Suppose there are 10 routes from Oyster to Manchester and 5 routes from Manchester to Newfoundland. How many routes are there from Oyster to Newfoundland passing through Manchester? So immediately from this question, we're using the multiplication principle because this is like a process. We're starting from Oyster to Manchester. So that's step 1. We're trying to get from Oyster to Manchester, right? Which road we're gonna take for that? There's several ways we can do that. There's several roads we can take. Step 2, we're getting from Manchester to Newfoundland. Again, there's several roads we can take to do that, which is why we're using the multiplication principle. So next, since we have 10 roads that go from Oyster to Manchester, so that means 10, and then 5 roads that go from Manchester to Newfoundland, all we're doing is multiplying the two because it's a process. Sometimes people describe this as like, and you're doing both of them. It's all part of the process. There's many ways you can get from Oyster to Manchester. There's many ways you can get from Manchester to Newfoundland, and you're just tying in the 2 ways. 5B. How many 8-bit strings have either the second or the 4th bit 1 or both? So I'm not even gonna lie, this question kind of had me, but we figured it out. We figured out the reasoning. Anyways, so we want to find, okay, how many 8-bit strings have either the second or the 4th bit being 1 or both, right? So the first thing you would have to consider is case 1. When the second bit is for sure 1, we're setting the second bit as 1. So that would mean that with the other bits, the first, third, fourth, fifth, sixth, seventh, and 8th, those can either be 0 or they can be 1. So there's 2 possibilities for the other bits. However, for the second bit, since we're setting it as 1, there's 1 possibility. So with that being said, we're just multiplying. So since we have the other bits having two possibilities, which is the 7 other bits having two possibilities and the second bit just having one possibility, that would simply be 2 to the 7 power. Similarly, we can set the fourth bit as 1 and say that the other bits can either be 0 or they can be 1. So the other bits, there's two possibilities, and with the fourth bit, there's one possibility. The fourth bit is just 1. The other bits can be 0 or 1. So of course, that would again be 2 to the 7th power. So those are two different cases, two separate, two independent events. So of course, with those values, would add them. However, with this, we'll have to take a step further and realize that both the second bit and the fourth bit can be 1 at the same time. Because in the first case, we're saying the second bit is 1. However, the fourth bit can be 0 or 1, meaning that there's some cases where within the 2 to the 7th possibilities, there's some cases where the fourth bit is also 1. And similarly, with the second case where the fourth bit is actually 1, the second bit is 0 or 1, and there's some cases where the second bit is actually 1. So with that being said, this is like an example of the inclusion exclusion principle, where, for example, we know our sets. We're trying to find the union of the sets, and we're identifying, like, for example, A union B. We'll have set A and we'll have plus set B. However, to get the union, you have to subtract the intersection of those sets. So there's no repetition of any element. So this is like an example of that. So considering that, we'd have to look at the case where both the second and the fourth bit is 1. So all we're doing, where we have the second and the fourth place, right, we're just putting 1 there because there's one possibility. However, the other placements, the other bits, positions, would have the 2 possibilities. So we'd have 2 times 1 times 2 times 1 times 2 times 2 times 2 times 2, and we would get 2 to the 6th power. So case 1, we'll have 2 to the 7th. Case 2, we'll have 2 to the 7th as well. So we'd add those two. So we have 2 to the 7th plus 2 to the 7th. And of course, we would minus our intersection being 2 to the 6th. And that would be our answer. So we have 2 to the 7th plus 2 to the 7th minus 2 to the 6th. And 5C, or final question for this video. A man has 8 pairs of shoes, 4 pairs of pants, and 5 shirts. How many different outfits are possible? So our 2 general questions: does order matter? Is there any repetition? So first of all, we know that the man has 8 pairs of shoes, 4 pairs of pants, and 5 shirts. And we just want to know the number of different outfits possible we can make with what he has. So for example, let's think about it. If we have a red shirt, black pair of shoes, and a blue pants, right? We'll put the red shirt first, then we'll put on the blue pants, then we'll put on the black shoes. Would that be a different outfit if we chose to put on the blue pants first, and then we'll put on the red shirts, and then we'll put on the black shoes? Would that be 2 different outfits? Would those be 2 different outfits? No, they're the same thing. So with that being said, order doesn't matter. We just care about how we put together the pieces of the outfit each time to make a different one. So since order doesn't matter, we know that we're dealing with combination. Next, is there any repetition of any element? So from here, all it's saying that he has 8 pairs of shoes, 4 pairs of pants, and 5 shirts. We can make the assumption to say that each pair of shoes, they're different. Each pair of pants is different. Each shirt is different. So with that, we can say, oh, we're assuming that there's no repetition. We're assuming that each piece of the outfit, each shoes, each pants, each shirt he has, they're all distinct, they're all different, there's no repetition. So since we know it's combination and we know that there's no repetition, we're just going to use the formula that we know, right? So each time we're choosing like a shoes, a pants, a shirts, we can choose one at a time to form the outfit. Because you don't want to wear 2 pairs of shoes, you want to wear 1 pair of shoes, right? Exactly. So with that being said, we can say, for starters, it's 8C1, that's for the shoes, times 4C1 for the pants, because we're wearing one pants at a time, times 5C1. And we're multiplying because it's a whole process. We're choosing an outfit, we're doing it together. We're not considering each thing separately. So since we have 8C1 times, what's the value? 4C1 and 5C1, I'll be multiplying together. That would simply just give us, if we were to write it another way, that would give us 8 times 4 times 5. And that would be your answer. And that's the reasoning for that question.